soul gel. If you want high surface area, porous material, one can use this soul gel material. Hydrothermal, solothermal method. This method one can use to prepare different nanostructures or nanodimensions. Means one can prepare quantum dot, one dimension, two dimension, and two dimension methods can be prepared this using this hydrothermal and solothermal technique. This hydrothermal method means what? This is the closed system where water is used as a solvent. Other than water, if you use solvent, then it is called as a solothermal method. But this method is what is the drawback of this method is you cannot scale up this method beyond few grams. So combustion synthesis, if you want highly crystalline material with high surface area, this combustion synthesis can be used. Here in combustion synthesis, key step is one of your reactant is act as a fuel. Then microwave synthesis technique. This technique gives us very nice homogeneously dispersed nanoparticles in large quantity. And then another one is sonochemical methods. In our laboratory at CMF, we are using hydrosolothermal, soul gel, as well as combustion synthesis technique. Microwave synthesis technique also we are using depending on our applications. So these are the various characterization techniques required for the analysis of our nanomaterial. So first is invisible absorption spectroscopy. Using this invisible absorption spectroscopy, we can identify the absorption behavior of our bed material. Basically, band gap of material can be defined using this spectroscopy. Then photoluminescence spectroscopy. Any kind of surface defect present in our system can be identified using photoluminescence spectroscopy. FTR spectroscopy, we are using different kinds of functional groups. If these functional groups remain on our surface of nanomaterial or completely removed, that can be identified using FTR spectroscopy. X-ray diffraction spectroscopy used to identify our material is formed highly crystalline, or amorphous, or we can identify its crystal structure. Then scanning electron microscopy used to see the surface morphology of our prepared material, whether it is one dimension, rod-like structure, or three dimension, or hierarchical structure can be identified using scanning electron microscopy. Transmission electron microscopy used to study the microstructure analysis of prepared material. And thermal analysis like thermogrammetric analysis can be used to study the thermal stability of our prepared material. Means before doing its reaction or doing its application, we can identify up to what temperature our material is being stable in that environment. So now we have seen its synthesis and what are the characterization techniques. Now we will see various applications of prepared semiconductor nanostructures. So first application is photocatalysis. Okay, one by one we will see next slides. In solar cell, nanoelectronic devices, biological uses, sensors, clean energy production, organic synthesis. Only few applications I have reported here. The application of semiconductor nanostructures is huge application, but whatever our concern I have noted here. Okay, let's see first application of semiconductor nanostructure is photocatalysis. Okay, so what is meant by photocatalysis? It is simple catalytic reaction involving absorption of light by catalyst or any semiconductor nanomaterial. In another word, we can say that it is advanced oxidative process can be effectively used for complete mineralization of organic pollutants and degradation of various dyes present in air and aqueous system using UV visible irradiation. Here the source UV visible irradiation means direct sunlight can be used. What is meant by mineralization? Here mineralization means whatever pollutants present in our atmosphere or water can completely convert into CO2, nitrogen and water. It is called mineralization. And what is degradation? Degradation means suppose we have some toluene, it's CH3 group, methyl group, it is benzene. It is called degradation. Means whatever its original form, it is converted into another form. So it is called degradation. Okay. In another word, photocatalysis is nothing but the acceleration of photoreaction in presence of catalyst. And basically, this photovoltaic reaction means redox reaction. Means simultaneously at conduction and valence band, their oxidation as well as reduction happens. Okay. So, as I told the application of photocatalysis, it has some advantages over the present techniques. Photocatalysis has the following advantages over any other or whatever existing purification techniques. As I mentioned earlier, that real destruction of pollutants rather than simple transfer into another substance. Means if you have to degrade some acetone, it completely degrades into CO2 and H2 rather transforming into another substance. Okay. Degradation of pollutant at ambient temperature and pressure. At ambient temperature, 25-degree reaction can happen and at 1 atmosphere. Okay. It is simple, less expensive, and relatively easy to fabricate, and this catalyst can be recycled anytime. In other words, it is economical, cheap, and lower energy consumption. And main advantage is that large number of pollutants can be degraded using this technique. So this is the first report. In 1972, these two scientists, Fukushima and Honda, reported this phenomenon for the first time. What they did, they have taken platinum electrode and TiO2 electrode. Okay. So on TiO2 electrode, they shine the light. As soon as they shine the light, they observe that generation of some gas on platinum electrode and some gas on TiO2 electrode. Later on, they analyze and they observe that there is a splitting of water has been occurred. At platinum, they are getting hydrogen, and at TiO2 electrode, they are getting oxygen. Since this first report in 1972 by Fukushima, enormous amount of people thinking to produce hydrogen using water splitting using sunlight. So this is the cheapest method to generate the hydrogen using water. Water is plenty and solar light is also plenty. But what is the main criteria? This catalyst, TiO2 is the main criteria, main heart of this water splitting. So this is the general reaction. See, water with the help of photon, hydrogen plus oxygen is formed. This is the what happened after absorbing the light. The electron pair is being generated, and this electron react with 2H plus ion. Hydrogen is being liberated at platinum electrode, and oxygen is being liberated at TiO2 electrode. So let's see the general mechanism of this photocatalysis. So this is the semiconductor material. It has some band gap. This is the valence band and conduction band. If you shine some appropriate light on this semiconductor, this electron present in the valence band absorbs this light and goes into the conduction band. And this electron reacts with H plus ions and produces hydrogen. You may say, well, from where this H plus comes? Water absorbs dissociatively on the surface of atoms. That's why it's H plus happens. Okay. And simultaneously, at the valence band, this OH radical is being formed. And this OH radical oxidize water into oxygen molecule. Okay. So this is one example we have seen, generation of hydrogen. These are the enormous amount of applications of photocatalysis. Light, plus here I have shown the example of PL, but you can use here another catalyst in any semiconductor oxide catalyst having band gap in the range of 1.5 to 3 electron volt. Okay. So first is self-cleaning effect, antimicrobial effect. Organic reaction can be performed using reaction. Then hydrogen generation. Hydrogen can be used as a fuel using fuel cell technique, antimicrobial effect, anti-fogging effect, USC degradation, and water treatment. So one by one we will see the application. So what is the basic requirement for the material to be having good photocatalyst? First one is the catalyst should be chemically stable. During the reaction, it should not react or it should not change from one material to another. Okay, the catalyst should be stable. So this is the first criteria. Whatever we are choosing some catalyst, it should be stable during the reaction. It has proper band gap. This band gap must be in the range of 1.5 electron volt to 3 electron volt. Other thing is that it has appropriate conduction and valence band potential. If its conduction band potential is more negative than the hydrogen emission potential, then only it gives us hydrogen generation. Otherwise, you may not get hydrogen from the water splitting. And whatever the electron hole pair is being formed after the effect light absorption, this charge separation should effectively occur. If the electron hole pair is separated, then we can use for further reaction. If it is recombined, then the photon may lose. We cannot get high photocatalytic activity. So this is the redox potential of various semiconductor materials. TiO2, constant titanium, zinc oxide. Let's see here. This is the conduction band level of the semiconductor. And this is the valence band level of the semiconductor. In case of TiO2, conduction band level is slightly negative than the hydrogen emission potential. So TiO2 can generate hydrogen using water splitting. But SnO2 cannot give hydrogen because its valence band, sorry, conduction band is little positive than the hydrogen evolution potential. So those materials having conduction band above this or more negative than hydrogen evolution potential can generate only hydrogen from water. So what kind we have generally four types of semiconductor materials depending upon its band positions. First one is 4 type, is what oxidation reduction can happen. The oxidation and reduction power is strong enough for the evolution of both hydrogen as well as oxygen, such as PiO2 and stone steel pattern. Second one is R type, only reduction power is stronger to reduce the water. Okay. O type, only oxidation power is stronger to oxidize the water. The X type means it has some weak oxidation and reducing power. This X type is comes low band gap material, is about around 1.5 to 2 electron volt material are caused in this reaction. And most useful nature of semiconductor 4 type. Okay. So water splitting mainly depends upon nature of semiconductor. Then nature of metal loaded semiconductor. People have in advanced means few reports mention that photovoltaic activities improve of present semiconductor by loading different nanomaterials on semiconductor. Then how these metals is being loaded on this semiconductor, that also affects. Then dope semiconductor and coupled semiconductor. These are the various processes one can enhance the photovoltaic performance of the semiconductor materials. We have seen that metal loaded semiconductor enhances the photovoltaic performance of semiconductor. How is palladium, platinum, rhodium, vitamins having high electron affinity? Okay. As soon as by absorbing the light by semiconductor, it generates electron hole pairs. As soon as this electron hole generates, this platinum, palladium, rhodium absorbs the or attracts the electron immediately depending upon its electron affinity for further reaction. So in this case, platinum is having high electron affinity, 2.12 electron volt. So as compared to this, platinum loading is more efficient or more pronounced for enhancing the photovoltaic activity. It almost increases the hydrogen evolution rate by a factor of 2 to 100. Okay. So these are the general methods how to load this metal on semiconductor. Simple one is you take your prepared semiconductor in the water, add your platinum or palladium or rhodium precursor in that as per your stoichiometric amount. Then it can be used using photocatalytic reduction technique. Then its loading must be in the range of 0.1 to 1%. You load more than 1%, what is happening? It acts as a shading effect. Means it blocks your photon reaching to the semiconductor surface. It should, one has to study its loading amount. If it is 1 weight percent, 5 weight percent, or 10 weight percent. Higher loading leads to fast electron hole recombination. So recently I have seen this application on the internet, the mosquito trap. Mosquito trap, what is happening? This is being coated with the semiconductor material like PiO2, UV light is still here, and they are using some tank. Okay. Whatever VOC is in the atmosphere, that is being oxidized to produce CO2. And this CO2 is being sensed by these mosquitoes, and they are coming in this area, so that with the time they are getting stuck in this capture net. So how mosquito bite human being? We are just exhaling CO2, and due to CO2, they are sensing CO2 mosquito, and with this sensing, they are biting us in the night also, or everywhere they are biting. With the same phenomena they have used here, and we prepare the mosquito trap. This is a nice example of our photocatalysis technique. So another one is hydrophilicity, super hydrophilicity. What is happening? You might have seen there is a huge buildings in the roadside with some glass or acrylic sheets. That sheets are being coated with such a our semiconductor material. So what is happening? Okay, so super hydrophilicity. If this material is in this direction, if you shine the light, it completely covers that surface area or wet that surface. How it increases the super hydrophilicity? It reduces the water contact angle to 0, and it creates surface oxygen atoms. In case of TiO2 or any other semiconductor, this electron hole phase has been generated, and this hole creates here oxygen vacancies on the TiO2 surface. And Ti4 plus is converted to Ti3. So here oxygen vacancy is being created. And on this oxygen vacancies, the water molecule is dissociatively adsorbed on the surface. So this schematic I have shown here. So these are the oxygen vacancies, and this oxygen vacancy, the water molecule is dissociatively adsorbed. As this is the semiconductor coated surface. As soon as the light strikes on that surface, whatever the dust molecule, the water is due to superhydroxide dust molecule removes with the water. So see, this is the one slide I have shown here. This is the TiO2 coated or semiconductor coated material, and this is normal material, normal wall. It is not coated with semiconductor. After 5 years, you see, this is the semiconductor coated wall. It is neat and clean, and whatever this is not coated, it remains dusty around this. What is happening here? Influence of light and moisture it self-cleaning effect using oxygen. Another is self-sterilizing effect. So TiO2 photocatalysts are used to kill the bacteria, and self-sterilizing surface can be prepared. Okay. The first report reported in 1997 with the help of E. coli. E. coli is the bacterial suspension. For this, how they have invented this or they find this? They perform one typical experiment involves placing 150 microliter of E. coli suspension containing 3 into 10 to 4 cells on illuminated TiO2 coated glass plate. And under this condition, there were no survival of cell within 1 hour. Means within 1 hour, all these cells will be killed. Killed means we can say it is deactivated. What is happening in this case? Whatever this electron hole there, it ruptures the cell wall of this bacteria or virus. With the rupture of this cell wall, this bacteria or virus are getting deactivated. So this technique also used for the cancer treatments. Here this house is being shown. Here these 2 tumors are there. The first tumor, they have injected the semiconductor material, and this is it's not injected with the semiconductor. After a few months, the semiconductor injected tumor is not enhanced or larger, but the tumor without semiconductor is growing very faster. So this can be used for cancer treatment also. So these are the other applications of this semiconductor coat catalyst technique, other than hydrogen generation, oxidation of volatile organic compounds, the removal of trace metals, removal of NOx. This NOx comes from our atom by exhaust, water treatment, and reduction of dinitrogen. Means one can prepare ammonia from absorbing from the reaction of nitrogen plus hydrogen using photocatalysis. Also, CO2 reduction techniques have been tried using this technique. Means from CO2 with the help of hydrogen, methanol, or some reverse reaction can be prepared using this technique. So this is the experimental setup we have seen for photographic hydrogen generation. So this is the round bottom flask. This is the quartz condenser fitted with mercury vapor lamp as a source of visible light, because every time we cannot conduct our reaction in sunlight because we have only 4 to 5 months sunlight, and it is difficult to compare our today's result after 1 month or 2 months because we have a large variation of temperature from 20 degree to 45 degree 1 year. So we have developed our own reaction setup. So this is the modified EDO-emitter tube. It contains our catalyst plus water. After starting this light, whatever this hydrogen and oxygen is being generated, with the help of this tube, it is collected in this EDO-emitter tube. And with the help of time, what is hydrogen, how much hydrogen oxygen is being generated is being calculated using this with the help of gas chromatograph. Okay. This is the same setup can be used for the degradation of various pollutants present in the water. See here, we can degrade the ppm level impurities in the water. If you directly with highly polluted water or any other material, we cannot purify it in this method. This method is specifically for purifying ppm level impurities. Means by other physical, chemical, biological methods can pure the material up to 95%. Whatever remaining 5% pure, that can be pure using this purification technique like photocatalysis technique. Okay. So now these are the basic things. Now I will show you some of the research that we have prepared in our laboratory and we check this photographic performance at electronic. Okay. So here we have prepared this PIO2 nanomaterial using hydrothermal synthesis technique. So here what happened? We prepared this anatase PIO2 as well as the PIO2 mixture. This is the SEM spectra which shows particle size around 5 to 10 nanometers, nicely distributed. This is the Raman spectra. It helps us to identify the anatase as well as the bright phase. This is the diffuse reflectance user spectra helpful to identify the band gap of the material. So this is the table indicates the band gap of material surface area. See what is happening here. The material prepared at 120, surface area is 182 meters square per gram. If we increase the temperature of this reaction, surface area drastically lowers. This is because at higher temperature the particles are agglomerated and some large size particles are being formed. Band gap is around 3.3 electron volt and the time degradation will observe. So whatever we have prepared at 160 degrees shows highest dye degradation, 6.32 into 10 to the minus 2. It's the rate constant. Okay. So within 2 hours, it completely degrades with flame blue. Okay. So this is how we check in the degradation of this methylene blue. This is the methylene blue dye 10 ppm solution. We have taken its invisible absorption spectra. Okay. So at 10 ppm, it is showing almost 1.6 absorbance at 60 nanometer. We are adding the PiO2 and we are shining light on this. And after every 15 minutes, we are removing the supernatant of this material. We centrifuge to separate the catalyst and we are taking this invisible spectra. After 2 hours, whatever this absorption will completely vanish. It means that our methylene blue dye is being degraded. Here I am using word degraded, not middle. Okay. So the next thing what we prepared synthesis of zinc oxide nanostructures. We prepared this using hydrothermal materials. So these are the hydrothermal reactors. This Teflon container and this is the stainless steel container where we are adding all this zinc nitrate, then sodium hydroxide in this material and we are packing it and we are heating it over. So here what we did, we are heated this at different hours, 2 hours, 4 hours, 8 hours, 12 hours. So here what we want to identify that. What is the influence of time on our catalyst activity? Okay. So we analyze the prepared material 2 hours, 4 hours, 800, 12 hours, and keeping reaction temperature constant 200. We observe that in all 4 cases we observe the formation of hexagonal zinc oxide nanomaterial. This is the usual absorption spectra. All shows the absorption peak around 380 nanometer, which corresponds to the band gap around 3.35 electron volt. This band gap is being found by E is equal to h mu. If you solve this equation, E is equal to h mu, band gap is equal to 1240 divided by wavelength in nanometers. So this wavelength you can use to calculate the band gap. Okay. So this is the FSM spectra. See here, the material prepared at 2 hours shows formation of hexagonal shaped zinc oxide. Nice zinc oxide, hexagonal shaped flexi will form. Further heating this material for 4 hours, 3-dimensional growth is being offered. See here, 3rd dimension is cubic or cuboidal shaped material is being formed. This is 2-dimension getting converted into 3-dimension with the help of rising the reaction temperature. So this is the schematic of our dye degradation setup. Already I have shown you this real picture. This is the mercury overlap quartz and this is the centrifuge stirrer and this is the dye solution we are keeping on it. So here whatever we prepared the zinc oxide, the material prepared at 8 hours shows highest photovoltaic activity. So within 2 hours almost it degrades 100% methylene blue. So why 8 hour shadow prepared at 8 hours shows highest photovoltaic activity among these other temperatures? Because for photovoltaic activity, not only the band gap is important, it requires optimum crystallinity, optimum surface area, and optimum band. So material prepared at 8 hours is having optimum band gap as well as surface area. That's why it is having higher activity. Another what we did, we prepared PiO2 and heated at 400, 500, 600, 700, 800. In case of PiO2 material is having 3 phases. analytic is stable to 600 degrees centigrade. Then rupile is being from 700 and above 700 rupile is from. We just want to check which case is having higher photoactivity activity. That's why because we prepared this material heated from 400 to 800 degrees centigrade. So here see, if the heat into another space at 25 degrees centigrade, the small pitch is to rupile. At 700 degrees centigrade, this analysis getting converted into rupile and at the higher temperature 800. So analysis was completely converted into rupile. Okay. So see the bandwidth of this material. The bandwidth of analysis varies around 3 electron volts and the mixed phase effect rupile it is 3.2. Okay. So we observe photocatalytic activity. The material features are 400 degrees centigrade shows highest photocatalytic activity for hydrogen. Almost 1200 micromoles of hydrogen is being generated from water species. So another what we do, we prepare layout which requires easy life for this application. So what we got further feasibility in the physical technique. So let's we put this layout with vanadium. What we do, we just added vanadium from 1 more percent to this reaction with the as we have said here, as we change the vanadium concentration, the analysis will factor. So this is a nice study we are going to look at. We keep temperature constant and we changing the vanadium percentage, this analysis getting converted to this percentage. How the temperature here is between the temperature is the valence band is made of conduction band is made of here. This valence just lower than the valence. Electron from this what we do
Sorry, sir.
yes, sir.
There is disturbance in the voice. There is disturbance in properly audible.
Hello, what my video so that you will hear it clear. Hello.
हाँ
आवाज खूप
It's clear now?
हाय
Hello. My voice is audible, sir?
हाँ हेलो सर सुधीर सर
सरांनी म्यूट केला तू
सुधीर सर unmute yourself. Arbuj sir. Arbuj sir. Hello. Can you hear me?
Hello. Sir.
Yes. 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 Now it is okay.
Am I audible now, sir?
Yes. Yes. Yes.
Yes, yes.
But there is some disturbance. No. 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 Wait, sir. त्याचा आवाज येत नाही ना?
Cannot audible, sir. Arbuj sir, आवाज येत नाही तुमचा.
Hello.
आवाज येत नव्हता. आवाज हा, आता येतो.
Now it is clear.
हा ठीक आहे.
हा, ठीक.
थोडी फरक not clearly audible. Okay. Arbuj sir. Hello. कसा आहे सर?
हॅलो,
त्यांचा आवाज येत नाही ना? कसा
अर्बुज सर.
दुसऱ्यांचा आवाज येत नाही ना?
हॅलो, नाही आवाज येत नाही सर.
हा सर, आवाज काहीच नाही, आवाज नाहीये. सर आवाज नाही येत, आवाज.
अर्जुन सर आवाज येत नाही, आवाज. Okay, dear participant, there is some disturbance in this internet connectivity. Sir, trying to resolve.
Hello, now am I audible, sir?
Yes, yes, now it's okay.
Okay, now okay, sir. Okay, so I'll just go 2 slides back.
Okay, okay.
So here what we did, we enhanced the photovoltaic activity of zinc oxide by loading silver with different weight percent. So here we loaded silver using from 0.51% to 10%. So in the spherical shape is the silver nanomaterial attached to the rod-like structure. So this XRD pattern, this indicates the zinc oxide material, and water peak around 38 degree it is due to the cubic silver material. So here what we observe that 10% silver layer is showing highest photovoltaic activity. It shows almost 95% degradation within 1 hour. So here whatever we prepared 10% silver zinc oxide composite shows this rate constant 6 into 10 to minus 2 per minute. Okay. It is almost 6 times higher than the pure zinc oxide material. So further what we did, we enhanced the photovoltaic activity of zinc oxide using loading series. So let's see the mechanism of coupled semiconductor. In this case, what is happening? 2 different semiconductors with 2 different band gap is being used. After shining the light, this electron hole pair is being generated in both the respective semiconductors. Okay, and whatever this electron present in the conduction band of one semiconductor react with the valence band of another semiconductor, and due to this electron present in the semiconductor material and hole present in this another semiconductor is available for further reaction. This hole react oxidize this ethanol or whatever sacrifice reagent for the oxidation, and it creates a CO2 and H2. Here this electron react with H plus ion, and it gives us hydrogen gas. So sacrificing one electron hole pair gives us one electron and one hole pair for further reactions. Okay. So here we prepared CDS, cadmium sulfide zinc oxide nanorods. As we enhances the activity of CDS, we are getting higher photovoltaic activity. So here we prepared PQ-TiO2 nanomaterial. This PQ is the pentasemiconductor, is organic semiconductor, and this TiO2 is inorganic semiconductor. So this is the TiO2 material, and we will vary its composition from 0.201 to 0.21%. So this is the whatever spherical one is TiO2 and sheet-like structure to PQ. So here we observe the same phenomenon of coupled system, and we observe that highest photovoltaic activity for 0.21% loaded PQ on TiO2. So here what we did next is we prepared cadmium sulfide at different temperatures. So we prepared TiO2 at 12 hours and 14 hours. So what effect we observe that this CDS, it's prepared at lower temperature or lower time. Its length is small, up to 200 nanometers. If you enhance the time or increase the reaction time, this micron shaped rod like morphology will form. Okay. So from Excel also one can see the specific orientation of the material. This is the small length zinc oxide rods, is usually 0.2 is high intensity. If its length is more, its 0.2 peak intensity is lower. Means one can see from the XRD only that there is some preferred orientation in the material. So another material will prepare tin sulfide. Flower-like structure is being prepared and its photovoltaic activity is compared with the TiO2 material. We observe that tin sulfide prepared is having higher photovoltaic activity as compared to TiO2. Okay. Nice rose-like morphology is being prepared, and its structure we have tuned using hydrothermal synthesis techniques. So now first application we have completed, the photocatalysis. Now the second application we are going to cover is solar cell application. So am I audible, sir? Or sir, am I audible?
Sudhir sir, you are audible.
Okay, sir. Okay, I'll continue with this. So solar cell, generally solar cell is being separated or categorized or divided in three generations. First generation solar cell, second generation, and third generation, depending upon its application process. In first generation, what is happening? Single crystalline silicon is being used. Okay. In second generation, instead of single crystalline, a vapor structure or film technology is introduced to prepare the silicon solar cell. In this case, what is happening? The amount of material is being reduced. Okay. And third generation is right now what we are doing at our laboratories. Perovskite solar cell, dye-sensitized solar cell, hybrid solar cell, polymer solar cell, quantum dot solar cell. These are the various sensitive materials which absorb the light to generate the electricity. Okay. So all these materials are now at the research phase, and all first and second generation materials are already in the market. So this is the schematic how the dye-sensitized solar cell is being formed. So for solar cell we require two electrodes, anode and cathode. Okay. So we are using fluorine doped oxide material. This is the one electrode. On that we are coating platinum. Then whatever the material we are using, semiconductor nanomaterial, it may be oxide or sulfide, we are coating it, and it is basically act as the anode material. Okay. So on this coating, one has to absorb the dye molecule, photosensitizer. So that may be some kind of dye can be absorbed on this material, and with the help of light, this material absorbs the light and it gives electron or hole is being generated, and this will transport to the respective electron and we will get some electricity. Okay. So this is the solar cells we are fabricating at our laboratory. So this is the working mechanism of dye-sensitized solar cell. So as already mentioned, this is the FTO electrode. This is the platinum counter electrode coating on FTO, and this is the material coated on this FTO. This is the dye molecule. It absorbs the light, and after absorption it gets into the excitation state. And when coming back, it gives electron to the conduction band, and this further is being transported to the load to produce the electricity. And this excited molecule is converted again. Oxidized and reduction technique has been occurred due to this iodide and triiodide technique, and it dye is regenerated for further reaction. So these are the basic formulas being used to calculate the efficiency of solar cell. See, if I prepare any solar cell at our laboratory, its efficiency should be same all over the world. So that's why it's some formulas are there. Power, this is a current density, this is the voltage, and this is the IPC, instant power conversion efficiency, number of electrons generated by absorbing the incident photon into 100. This gives us the some number that can be compared with the other prepared solar cells. So here what we prepared TiO2 material using hydrothermal method, and this is the SEM spectra and TM spectra. Nice plate-like structure is being formed with the length 5 to 10 nanometer, and this is the solar cell we fabricated. So what we observe here, this is the standard sample, Day-01 25. So here we observe the standard sample efficiency is around 2.23 electron volt. Okay, and this IPC is 40%. So TiO2 we prepared, its efficiency is almost 4.31 electron volts, almost double than the prepared double than the commercial Day-01 TiO2 material. So further what we did, we prepared zinc oxide nanomaterial with varying the concentration of cathode. So here what we observe, some video structure is being formed. This is the TM spectra, and this is the solar cell fabricated using prepared this material. So commercial zinc oxide is giving efficiency 0.66. Zinc oxide prepared with capping, without capping, its efficiency around 3.56. It's almost 5 to 6 times efficiency is being enhanced. You see the effect of material synthesis, how it enhances the efficiency of solar cell. So this is the about high sensitized solar cell. Another one is hybrid solar cell. What do you mean by hybrid solar cell? So to process in a solution mode, to make it thin film, we are going to use this polymer semiconductor material along with our inorganic semiconductor material. And this polymer semiconductor, it forms the composite with inorganic material, and we get a nice electron movement from conduction band of one electron from one semiconductor to another semiconductor and to the respective electron material. So advantage of this hybrid solar cell material is that whatever this active material, its thickness is only 150 to 200 nanometer. This so small active material is being used. If it works about 10% efficiency, will require very small material to fabricate this kind of solar cell. It may reduce the cost of solar cell. Okay. So these are the various processes involved in fabrication of hybrid solar cell. You have to clean the substrate, then spin coating, then loading of some pre-dot PSS, whole transporting this active material, then glow box. We have to deposit aluminum cathode material, then we have to seal this material, and then test the material. It's for fabricating one cell, you require 2 or 3 days come to testing. Okay. So these are the cadmium sulfide nanometers we prepared at CMET. So here, this is the nice 5 to 10 nanometer nanoparticles separated from each other. We fabricated solar cell and its efficiency is around, and we are getting its efficiency around 1%. Okay. So this is another application I want to cover is lithium-ion batteries. Okay. At CMET, we have full-fledged facility to fabricate button cell, coin cell, or pouch cell. Now everyone is having mobile, so in that mobile you have the battery. Okay, that lithium-ion battery. So at CMET, we are fabricating this anode, cathode, as well as full battery. We have fabricated this prepared nanomaterials. So these are the various steps involved for the fabrication of this kind of button cells. Okay. So these are the facility available at CMET. These are various instruments for fabricating these battery, lithium-ion battery at CMET. This is ball mill, this mixture coater, this vacuum oven, this roll press, this is scaling machine, this is glow box where the actual cell is being fabricated or sealed, and this is the battery testing unit. This here we can test our cells recyclable up to 100 cycle or 1000 cycle. So this is the one more example of semiconductor. This can be used for carbon-carbon coupling reaction. Okay. So this semiconductor photocatalysis can be used to fabricate this kind of reactions or organic synthesis. Here we try carbon-carbon coupling. What is this egg reaction? It is nothing but the reaction between aryl halides and ethyl acrylate. It gives us trans-ethyl cinnamide or cis-ethyl cinnamide at room temperature. Okay, using this catalyst. So See, this is Day-02 material, and this palladium having size around 2 nanometer or 6 nanometer is being seated. This is the catalyst used before reaction, and this is catalyst images taken after the reaction. Means before reaction, after reaction, palladium remains on this reaction. This is the advantage of this heterogeneous catalysis. What is happening in homogeneous, this palladium may leach out in our product. So this is being reduced by this technique. So to address the present pandemic situation, we have fabricated this kind of antimicrobial coating based on our nanomaterials. And we fabricated some antimicrobial mask, and we tested its towards Bacillus bacteria, Soros bacteria, and we have distributed almost 2,000 masks to various hospitals and public sectors like police stations and other. So we see here these are the masks. And after coating, we develop some coating, nanomaterial based coating. It looks like this, and we have tested here. See, this is the cloth piece, and the growth is being hampered around this cloth. Okay, so this technology is ready for transfer. Few industries approaches to this technology. So, being social responsibility, we have developed antimicrobial coating, and this coating can be applied in the hospitals for your fabric bedsheet. So see, this is the first virus we came to corona. In near future, maybe another virus may come. So this antimicrobial fabric, development of antimicrobial fabric is important. So this kind of technique can be utilized for fabricating antimicrobial fabrics. Okay. So I am at the end of my presentation. So at last, I will just inform you how you will get opportunity to work in it. So currently, we are hiring BSc and MSc students with specialization in physics, chemistry, and electronic science. We are just allowing them to perform the project at CMET, where they are hiring the chemical, metallurgy, and ENTC for our different projects. We take in nanotechnology. We have various students, PhDs in physics, chemistry, electronic science. CMET also recruits project staff during the fields. For more details, you see this our website. Okay. And at last, thank you. I would like to thank Ram sir, Pawar sir, Rasai sir for giving me opportunity to present my work here. Also, Gadwe sir and More madam, and I'm thankful to Pandale sir for giving me opportunity to present my work here. Thank you, sir. Now, if students have any question, please.
Yes. Now, thank you for elaborating this. Now, I request our students to please any query regarding this discuss. And this topic is open for discussion.
Hello.
Unmute yourself and then ask questions. Unmute yourself. Going to ask questions. Anybody want to know anything regarding the presentation? Okay, Sudhir sir, I have one question.
Yes, sir, please.
Okay, what is the maximum efficiency of reported in solar cell?
So at CMET, we reported 6% efficiency using TiO2 material.
Or TiO2 material?
TiO2 and our N719 standard dye, we have used ruthenium based dye material.
Ruthenium based dye material.
But for hybrid solar cell, we are not getting higher efficiency because there are some critical issues. In hybrid, what we are doing, we are using quantum dot material, and this quantum material is having some organic layer. So this organic layer hampers the electron hole pair transition from organic to inorganic. So we are trying to remove some 50% organic material from that capping, so that this proper contact should happen between organic and inorganic material.
Now we also discuss about the carbon-carbon coupling, that is heat reaction, by using this catalyst. That reaction also carried out in your laboratory?
Sorry, sir, I didn't get your question.
Heat reaction we carried out.
Heat reaction. So we did this heat reaction using palladium loaded TiO2 nanomaterial in presence of light. So this material, this reaction is we already reported in the Journal of Chemistry. So here what happened, as compared to your conventional technique, we required 3 hours at high temperature, 150 degrees centigrade temperature we required. So this temperature drastically reduced to room temperature, around 45 degree, we perform this reaction.
That is the beauty of that reaction.
Yes.
We perform in lab.
Yes, sir.
Why we need a catalyst or source of that reaction?
But sir,
Light. We perform the reaction in presence of light, na?
huh. So we use the light or molecular photon radiation, and the catalyst size is whatever palladium we loaded, its size is around 2 to 6 nanometer. On TiO2 particle, its size is around 100 to 150 nanometer.
Yes, yes. Okay. Anybody want to?
हॅलो अर्बुज सर.
Rasai sir, please.
हा, ते मॉस्किटो ट्रॅप ते बनवलेत म्हणतात ते त्याची सांग कॉस्ट काय आहे?
Cost is cost I haven't seen on the internet. It is just you put on internet mosquito trap, photocatalytic mosquito trap, you will get that picture.
What about cost of that?
Cost maybe I think it is few thousand rupees, maybe not beyond 5,000.
5,000 rupees.
Yes.
Okay. Thank you.
Anybody? Okay, there is a thank you Sudhir for this discussing all these different topics in this your lecture. So started from this synthesis of semiconductor oxide like TiO2 and ZNO, and it's a different procedures are there. So also discuss about the characteristic techniques of these oxide material by using XRD, PDIS, PL, FSM for the morphology, structure determination, and backup calculations. Sir, also throw the light on applications of the semiconductor material for in case of the photocatalytic degradation, water splitting, and also generation from the hydrogen gas. So important fuel for the new next generation. There are also discuss about the different types of solar cell, that is the solar cell, the work on that and there is also discussion about working mechanism, how to light is converted to electricity. Now efficiency is also got near 6% efficiency for ruthenium-based the solar cell. Sir also discuss about the working model of lithium-ion battery. What are these facilities available in the lab? Now we also touched one of these reactions carbon coupling. That is great reaction, and one of the beauty of his work or estimate, he prepared the road near about 20,000 by antibiotic coating, and it is distributed to workers. This is one of the important work of estimate, and it is also helpful for these workers to save their life from this coronavirus. Okay, this is regarding this presentation by this Arbuj sir. Okay, we are also apologizing the type of some internet connectivity issue and disturbance in the noise. Due to this bad weather, I have the internet connectivity also very weak, and that's why there is some disturbance in the midwife in your lecture. So I hope we resolve that issue in tomorrow's lecture, and participants of number near about 80 the beginning, and some participants are on YouTube. So we are taking limited participants in the mobile meet because of there is some disturbance to avoid the disturbance in the lecture, and more number of participants are we manage at YouTube link. So this is from this our side. I thank you to accept Dr. Sudhir Arbuj for the debate to accept our invitations and deliver the talk of our students on the occasion of 81st birthday of Honorable ex-Union Minister Agriculture Minister of India and ex-Chief Minister of Maharashtra. I also thank our PA office bearer and our principal, Dr. Amay Kandage, Vice Principal Sandhya sir, and giving the permission to arrange this lecture series of chemistry, online lecture series chemistry. And today is the first day, and our speaker is delivering this hot topic about synthesis semiconductor materials in applications for the various fields. So I again thank our stage guests and all participants, our students and participants from the various colleges from the Maharashtra, from the CO2 clinic as well as the Google Pit. So I thank again all our staff members from the chemistry department which organized series. Rasai sir, head of the department, and More madam, deputy star coordinator of our college, also giving us information about the deputy star activities. So, thanks to one and all for this coming to participate in this lecture series. Also, I thank to especially Bhagya sir because of all technical responsibility regarding this and also other colleagues for this taking responsibility to organize this lecture series. Okay, tomorrow at sharp 6 p.m. We start with another lecture from this resource person. So I request all students and the staff members to join before 6 o'clock to the second lecture of this lecture series. Okay, that's all, sir.
Thank you, Arbuj sir, for inaugurating our lecture series in chemistry. Thanks again. Thank you.
Okay,
Thank you all.
Thank you.
Thank you, sir.
Okay, this is from